Okay. So how do we negotiate some of the properties that might be averaged between these two materials? Well, there are two main approaches. One that applies what's called an isostrain condition, where you assume that forces are transferred from the matrix to the fibers perfectly, and that there's good intimate bonding between the two. Okay. Another is the opposite, where there might be poor distribution of the forces on the matrix into the reinforcement. Okay. And so in the graph shown here, we have the modulus of elasticity, or Young's modulus, capital E, again plotted against, say, the tungsten concentration in that previous tungsten carbide cobalt composite. And so to predict the properties, it would make sense that if we were at pure cobalt at 0% tungsten, that the properties of pure cobalt would be down here. We would have a low modulus metal in that regard. And then if we had pure tungsten, that this higher modulus material would give us our upper limit here. And how we establish the data between these two limits is given by bounds that assume either the isostrain or the isostress conditions. So the upper bound, often aligned with the terminology isostrain condition, shows that the modulus of the composite, where we have a mixture of these two limiting materials, is a weighted average between the two, where we use volume fractions to dictate how much of the property of the individual components is added to make up that of the composite. So we see here that Vm is a volume fraction. So we know that this volume fraction must be less than 1 and greater than 0. And so Vm is here for the matrix, the volume fraction of the matrix. And therefore Vp would have the same bounds, so it should be between 1 and 0. And so here we'll use P for particle. And the total volume is going to equal Vm plus Vp, and this is going to equal 1. Okay, so that is in absolute volumes, capital Vm divided by capital Vm plus capital Vp would be the volume fraction, lower Vm, for the material. Okay, and same goes for the particles, where we would swap p's to the numerator here. Okay, let's clean this up a little. So knowing that, we see here that the modulus of the composite is going to be a weight fraction of the matrix times the pure matrix modulus added to similar product of the volume fraction of the particles this times the modulus of those particles. And this gives us a nice linear relation between the two upper limits and a more predictable weighted average outcome between the two limiting modulus values for the matrix and the particles in this case. Now a lower bound can also be determined, where perhaps bonding and force transfer from the matrix to the particles or fibers is not ideal. And so the lower bound follows something similar, in that this time the volume fractions are again used as coefficients, but they are multiplying against the inverse of those modulus values for their respective components. So again, the volume fraction of the matrix divided by the modulus of the matrix is added to the volume fraction of the particles divided by the volume fraction of, divided by the modulus of the particles. And that sum is the inverse of the modulus of the composite. Okay? Some of you who have experience with resistors in parallel may recognize the format of this equation. And in fact, the property of resistance can be predicted to be following this isostress type condition that we use here for understanding mechanical properties. Okay, so with that, you might say, okay, so these are two bounds. We might expect properties to exist between the upper bound and the lower bound, depending on processing conditions, the type of bonding between these two materials, etc. And so when you do that and you actually take and realize these materials and study them and put all the data for actual real composites, you'll see that most of the data is in fact bound by either the upper bound or the lower bound. So that is, the data exists between the red and the blue curve. And so using these approaches for quantifying how the properties are averaged between the matrix and the particles that blend together to give us the composite does a good job of framing where we would find the properties of the material. So if bonding is very good, or if particles or fibers are aligned with the direction of the tensile force, for example, data points might be closer to the upper bound. If bonding is weak or the force is orthogonal to the main length of the reinforcement, you might be closer to the lower bound given by the isostress condition. Okay, so this property averaging, again, is very useful. In terms of extending it to fibers, it can better explain how longitudinal forces and transverse forces impact how the modulus in the material would be. So you can imagine we would have a longitudinal composite matrix, or a modulus for the composite that is transverse, comma T. And depending on how one loads or puts a stress onto the specimen, either in the longitudinal or the transverse direction, we may calculate the limits for the modulus differently. Okay, so to sum, we've seen that these approaches are a way of weight averaging the moduli of the components. In this diagram from your textbook, we have the matrix modulus defined as EM. We have the matrix of the fibers defined as EF this time. Okay, contrasting to the previous very close example of EP for particles. And the isostrain condition, where it is better aligned with parallel loading. So that would be the longitudinal mode. So if we're applying stress parallel to the fibers, that we're going to get a greater contribution to the net modulus of the composite if we load parallel to those fibers. Similarly, the isostress relation is going to speak more to the modulus of the composite should we be loading transverse to the composite specimen. And so if one were needing to understand how there was a discrepancy between modulus in one direction versus another, mechanical test work could identify that perhaps fibers are more oriented in one direction versus another, given how the composite was made. And as we mentioned, this approach can lend itself to other properties, not just mechanical properties. So for example, volume fractions of the matrix and fibers can also be used as coefficients on properties like diffusivity of the matrix, diffusivity of the fiber, to speak to the ultimate composite diffusivity, or even thermal conductivity can also be used this way. And even Poisson's ratio can also be predicted this way based on a matrix and a fiber component coming together. The lower bound relation mathematically can kind of be readjusted to look like the following. And so that again can be used to speak to lower bounds of diffusivity or thermal conductivity properties, or even electrical conductivity or resistance properties like we've touched on a moment ago.